paint house problem. Is there any question?
Oh, wait, I have one question.
Sure.
Yeah, so can we identify what's the objective of the problem before getting to know what it would cost function or
Yeah, sure. Yeah, but you know, I need to define all the assumptions, and then I will talk about the objective. Okay.
Okay, sounds good.
Yeah, sure. Yeah, thanks. So we want to go, and the name is paint house 2. So I said given is, you have to know, first of all, you have to be careful and to be sure that you understood all the assumptions, the givens. We said we have n houses, k colors, and we have a cost matrix, which is n times by k. And I was talking about in a cost I and j is the cost of painting house I by color j. Okay, so it means that for every, we have k colors, and painting every any house with that color, we have a cost for that. So what is the objective? Objective is find minimum cost to paint all houses. But we have a constraint which is really important. You have to be careful in DP problems so that there is no, there are actually, let me, the grammar, there are no neighbors with the same color. Okay, so, and this part, you know, that you have to know all the assumptions, first of all, and what is all your inputs. And the objective is to find a minimum cost. We want to paint all houses. And this is really important constraint. We don't want to have same color for neighbors. And if I go in with using only one really simple example to show you what is the, to have more sense for this guy, for this question. Let's say we have a cost matrix is equal to, let's say we have a matrix like, you know, 3 by 3. It means we have 3 houses and 3 colors. Let's say we have 1, 5, 3, 2, 9, 10, 2, 4, 5. So we know that n is 3 here, k is 3, and we have costs. So I want to color all of these guys. For house number 0, I can select, you know, I have 3 options, right? I have 3 options to color the first one. So let's say I want to do this manually, solve this manually. I select 1 because it is minimum cost, right? And the second house, I cannot select the same color. So though actually 2 is rejected, right? 2 is not my valid color. So I have to select 9 or 10. So let's say I'm selecting 9. And for the last one, I can select 2. Because now my colors will be 0, 1, 0. And 2 neighbors are not same color. We don't have any 2 neighbors with the same color. But this is this the minimum cost? Actually, I did in random selections, right? Definitely, I think because I can see, you know, for this guy, for these selections, the cost will be 1 plus 9 plus 2, which is 12. But I can see better selections actually. how do you think which combination will be the optimal solution, optimal answer for this problem? I'm going to go by example, and then we'll dive into the approach. Let's say,
one, sorry.
Mm-hmm. Go ahead.
Yeah.
One.
No, not one. 2, 0, 1, like 3, 2, 4.
2, 0, right?
And
2, 0, and this one, right?
Yeah.
Beautiful. If we select, let's say, yeah, beautiful. That's correct. If I select, let's say, with the other color, you know, I can select this guy, and this guy, and this one. I will have 3 plus 4 plus 2 will be 9. It is minimum, less than that. So as you can see, we cannot really find, you know, even manually the best one without trying all combinations. And when you have some questions like this, you know, I have lots of students that they say, how can I detect I have to use DP pattern, dynamic programming. Actually, for the questions that you want to find minimum, maximum, in most cases, DP is the, you know, the pattern you have to use. Especially, you know, when you have some constraints like this we have here. It is like an optimization problem. We have an optimization problem and we want to optimize it, and dynamic programming is the one of, you know, the really optimal approach to solve optimization problems. But in some cases, we can use some heuristics to solve, you know, the optimization problems using the min heaps, max heap. And I will show you in next sessions that the problem is really similar to DP problems, but you can solve much more easier using min heap or max heap. And we name this as a heuristic approach. But in most cases, when we have an optimization problem, as you can see here, you know, we had, you know, some try and errors here, and we detected we need to check all combinations. It is kind of finding the permutations, find all combinations for a specific problem. So we have a search space, we have to sweep, you know, we have to search, you know, all search space. In this case, you have to detect, detect that I have to use DP. And in order to solve DP, please go over, if you are interested, I cannot force anyone, go over top-down approach. In top-down approach, we go recursive solution, and we find the sub-problems. For example, here, let me go to the next whiteboard. I want to have, you know, the background. It helps me to write more clean. Let's say we have 0, 1, 2, 3, 4, and these are our houses. Okay, and we have K is equal to, let's say, you know, 3 colors. And we have the cost matrix. I don't want to talk about the cost matrix. I want to formulate the recursive formulas. So let's say, and I want to color all these houses, right? I want to color this one and then go to the next one and next one and next one and next one. So it means that I need an index, right? Because, you know, the main function will be like, you know, define min cost. And we have only cost matrix as inputs, because based on that, we can detect N and K, right? The number of rows is N and the number of columns is K, which is the number of colors. The first step, the first thing we observe, we need one more variable, which is index, which is I, okay? So I need one more variable to formulate my recursive. So let's say my index is pointing 0. How many options I have? K, right? Because I didn't color yet, right? I didn't paint yet. So if I'm in I have K, 1, 2, let me write from 0, 0, 1, 2, to K minus 1 options. So it means that I have K options to select it. And then in the next step, I will increase my I because I wanna go and paint house 1. And how many options I will have for this guy? K minus K, sorry, go ahead.
Oh, saying K minus 1?
Yes, K minus 1, because we have a constraint that we cannot have, you know, 2 neighbors cannot have same color. So it means that when I'm in my I is, let's say, more than 0, is 1. If it is 0, because we don't have any previous color, we can try all colors, right? But if I is greater than 0, I need one more variable to detect valid colors. So it means that we need another variable, which is previous color. And in the next step, I will have K minus 1 colors. And which color is my, you know, invalid is the previous one. And as you can see, we see how we can formulate our, you know, the sub problems. And we know that what will be the inputs, I and previous color. If I select, let's say, for the 0, I'm selecting this guy. And if I increase I to I plus 1, and the previous color will be the color I set for cell 0, right? And then I call the remaining of my problem with a starting index of I plus 1, and it is exactly self-similar problem to the original problem. And this is exactly, the signature of my function is exactly the same as the original one, which has I and previous color. And this is the way you have to detect how you can formulate the recursive formula. And this is the most critical part of the DP problems. If you want to go over, you know, you go solve it using top-down approach. So we detected that we need I and previous color. So it means that I need to return, I cannot use the original function I wrote here, right? I cannot use this. Let me write down here to have more space. Min cost and cost. And cost is a matrix. So I know that I need a helper because I need 2 more variables, I and previous color. So that's why I want to return helper cost. What is the initial I? 0, right? When we want to start our recursive calls, we want to start from 0. So this is I0, which is index. And what is the previous color, initial previous color?
K minus 1.
It is -1, right? Because we don't have any color. And we have to detect, we have to find a number which is not valid color, right? So yeah, this is -1 because we don't have any color for the previous color for the first first house. Okay? So based on, you know, some, you know, first, you know, analysis, we can detect how many inputs we have. So let's go and define helper cost I, and let's say previous. I'm gonna write, yeah, this is the previous. I'm gonna make it a little shorter because of the space. Yeah, I cannot. It is really difficult to write some meaningless variables. So the previous color. So as always, I don't want to write, the base case at first. After I formulate my recursive formulas, it is much more safe to define your base case. But before that, I want to calculate the number of rows and number of columns. I'm assuming the cost is not empty. At least we have one row. But if you do the code in the LeetCode, in order to pass all the test cases, you need to check also if the length of cost is 0, return 0, right? But I'm assuming the cost has at least one row. So n will be len of cost. Okay, which is number of rows, which is number of houses, and k is equal to length of cost 0, which is the number of columns is equivalent to number of colors. And I want to put some space here for base case. If you have more experience, you can write exactly at first, but I prefer to do this after I'm formulating my recursive part. So if you remember, we want to find the minimum cost. It means that I need one variable to keep the minimum cost for all tries, for all combinations. I need to keep the minimum cost, right? So that's why I want to define a variable minimum cost. This is the exactly same name of the function. It is better to, let's say this is the minimum cost, right? I use underscore, actually in Python, we have to use underscore, underline. Okay, so what will be the initial value for minimum cost? I want to update at every recursion call the minimum costs by applying the minimum of the previous value with the new value. So neutral value for minimum is infinity, right? Because minimum of any number with infinity will be that number. So that's why we have to select the infinity as initial value for this one. The float of infinity will be my infinity. And we talked about it, that we need to try all combinations, all possible colors for a specific index, right? Let's say I'm right now in index, let's say that my I is equal to 2. Let's say I is pointing to 2. I want to try all colors except previous color, right? So it's time to write a for loop, right? Because we want to try all combination, all possible colors. I want to write for color in range k, right? So we have 0 to k minus 1 colors, but I have to check because of the constraint that we don't have any same color neighbors, right? I will check if this color that I want to try for my current index or current whole house is not equal to previous color. If it is not, it means that it is valid color. This is exactly the pattern, if you see, is exactly like Sudoku solver we had previous session, like 8 queens. Inside of recursive call, we have a for loop because we don't have only 2 subproblems. When you have a binary tree, always we have two subproblems, left subtree and right subtree. But for hard DP problems, we have 4 inside of the recursive calls. This is exactly same. The pattern of this problem is exactly equal to the Sudoku solver. And we have some valid values we had in, in the previous, sessions, probably. Only the context is different, but the approach and what we are doing is exactly the same. So if color is not equal to previous color, I think I need more space to write down this part. Oh, I don't know. Can I? Let me first erase these parts because these are all explanations I did before. So the reason I'm trying to switch to larger screens is for these difficulties that I have in my online teachings. Okay, I can move this here. Now I have more space. I have a little more space on top. Okay, let me bring some notebooks under my hand to write easier in the bottom part. Okay, so if this is not equal, I can select this color. Oh, sorry, this color as the color for current house, right? So, and what will be the cost? I have to update my cost, right? Let's say we have a current cost will be equal to, I'm selecting for I, the house I, the color, and we know that if I use the cost matrix, I will find the cost of this selection, right? So I will write here cost I, which is my input here. I want to calculate the cost of minimum cost if I want to color my house as a starting index I. I will write I and color plus. So this is my current cost for my current selection, and then I will call a sub problem. What is a sub problem? Is a helper. Cost is a matrix, is a constant matrix. I have to pass it, and I have to increase I, right? I want to go to the next house. I plus 1. And what will be the previous color? The previous color will be the current color, right? For the next item, which is color. Okay, that's it. We do this. And then I will update because I want to keep the minimum cost for every combination. So I will write minimum cost will be equal to minimum cost and current cost. Okay, and we have this. And if you try, actually we try, let me write a comment here.
Yeah, Wahid, can you please explain again why you choose cost I color?
Oh, okay, sure. Yeah, I will explain it. Yeah, thank you. Try all possible colors to paint house I, right? We want to try all possible colors. So all available colors are from 0 to k-1. But I cannot use the previous color, so that's why I'm using the if statement here. So let's say I'm selecting the color number, let's say starting 0, 0, right? I have to know what is the cost of the painting of the house I with the color number, in a color, right? Actually, the color is starting from 0 to k-1. This is the cost of painting the house I with this color. And I have to add plus the cost of the remaining sub-problem. What is the remaining sub-problem? Is the next index, and the previous color will be the current color, okay? This will be the current cost if I try the first color for index I, house I. And I will update minimum cost here. In the next round, in this for statement, for loop, I will go to the next color. And again, I'm assuming I'm painting the house index I with color, with this color. And again, I'm calling the remaining problem, which is my sub problem, and updating the minimum cost. In the next round, I will go to the next color, right? We are trying all valid colors, calculating the minimum cost for them. And the good point, and the really important point here is this part, let me use my pointer. You shouldn't think about this part, what's happening inside of this recursive calls. This is the really the point that the most people dive inside of this recursive call and they don't handle the recursive solution. You don't need to think how it is calculated. You can assume what is the minimum cost. We assume that the helper is returning the minimum cost starting with index I, if you want to color, if you want to paint all of them, right? So I'm saying if I select the current color, which is this color, I think that the C is much more better than color. Let me change this to C because I'm saying color. It is a little weird. Let me change the name C. And here we will have C also. Okay, that would be much more better, if I'm, when I'm explaining. Okay, so for C, the color C will start from 0 to k minus 1, and we are trying all of them, and we are calling the remaining problem, and we are updating the minimum cost. Did you get the answer right?
So this is the cost, the 2D array which we defined, right?
Yeah, exactly. This is
okay.
the cost of painting house I with the color C that we are selecting right now. Okay, we are updating this, and we are going to the next round, and we try all of them.
Mm-hmm.
But here, if you remember the last session, we had backtracking, right? We had, because right now inside of this one recursive function, we call for several times. But right now, in the inputs, we don't have any data structure. All of them are some integers. They don't pass by reference. The copy automatically is passed in Python. And also, even in the other languages, it is strongly recommended for integers, for like, let's say we say primitives. It is recommended to pass by copy, not don't pass by reference. Because we don't have any variable which we are passing by reference, you shouldn't worry about that, because they are going by, we don't change any of the variables here inside of this guy, okay? And the cost is a constant matrix. So we don't need to do any backtracking, and it is done. We are trying all of these guys. At the end, we will return minimum costs.
So just a quick basic question. So when we decide, what is the pointer to decide whether we have to do backtracking or not to do backtracking?
Mm-hmm.
If you have any quick.
Yeah, sure. I will explain. So the first important point is you have to, let me finish the base case to finish the code, and then, I will explain for that general question, right?
Yeah, sure.
Okay, yeah, because, it is, I want to have it really consistent. Okay, so now it's time to find, write the base case. So look at the recursive calls. We have the only place we have recursive calls here. We change color. Yes, we change C. Every time C is changing, but it is not critical. So color can be anything, right? And only we have a constraint, we check here. We don't need to do anything for C in base case because we check the invalidity, condition here. And cost is constant. We don't need to worry about it. The only thing is I plus 1. And it is increasing. Because it is increasing, so we need to do the upper bound for this. Upper bound, right? So what is the upper bound? I, if it is n, will be out of range. So that's why we can write here I, if I is equal to n. So it is out of range, and we have to check it. So what should I return? First, you have to detect what's the type of the return of the helper. It is integer, right? It is integer. So I have to return integer. So the next step is to think about the problem definition. We want to return the minimum costs for painting all paints, all the houses. So let's say the index is pointing here outside of the houses. We want to paint all houses, but the starting index is outside of the all houses. What will be the cost of painting all of these guys? 0, right? We don't need to cost anything for this guy. And so we have to return 0. So detecting the condition of your base case usually is really easy. And you can do that. So let me connect my adapter, to, sorry. So I need to connect my adapter. Okay. Okay. And for the return part, you have to revise. You actually, rethink about the problem definition. If my I is n, what is the minimum cost of painting? It means I'm done, and I shouldn't color. I shouldn't paint any in a house, so that I have to return 0. That's it. Okay, and now our the first the first step, which is brute force, is done, and I will talk about time complexity and space complexity before But before that, I want to talk about when we use the backtracking and when we don't need. So for backtracking, first of all, you have to check. The first step is to check check 1. The first check. If you have more than once, if you have more than one recursive call. So for example, here we have k recursive calls, right? So you have to be you have to have some concerns about the backtracking. And in check 2, you have to check the variable types, the input variable types, input variables. When I'm saying variables, because we have some inputs are constants, you shouldn't worry about them, but you should only worry about the inputs that are changing. So, and then for variables, you have to check if let's say I want to do this here. The variables are some the integers, float, or let's say the string. This kind of actually not a string, the float is all of the primitives, right? Or we have some data structures. If you have some integers like that, like we have here, you shouldn't worry about backtracking because they pass by copy. These guys pass by copy. You shouldn't worry about it. But if you have data structures, by default in Python, they pass by reference. And even in our languages, if you can pass by copying, it is not recommended because you increase your space complexity. In these cases, if you want to pass by reference, you need to reverse any change you are doing after you call your recursive call, like we did in Sudoku solver. We did for 8 queens in the last session. Was that answer for your question?
Yeah, kind of, yeah.
Yeah, actually, you have to, if you don't have any data structure, I mean, you have some primitives, you shouldn't worry about it. Even if you have data structures, you can pass by, by copy, make a copy of them. Also, you don't need to backtracking, but you are doing in cost of increasing your space complexity. Okay, that's why we need to pass by reference, but we have to revert it, because when you pass by reference, you change that that data structure inside of your recursive calls, but you don't need to have the changed version for the next recursive call inside the for loop. Okay.
Okay, can you explain the first point, like the more than one recursive call?
Oh yeah, the more than one. Sometimes inside of our recursive function, like let's say here, we have only one recursive call. We don't have several recursive calls. You shouldn't worry about that. You don't have any backtracking. But if you have, let's say, a helper of this, and then in the next step you are calling again another helper. Okay, like we do here. It is like sequential helpers, right? That's why when every change we do before our recursive call, we have to do revert it after our recursive calls, because we have another recursive call in the next round inside of my whole function. Does it make sense?
Yeah.
But
so
go ahead.
So I think in one of the classes, we also talked about binary trees, right? So even there, when we have left off, like the helper of root.left and helper of root.right, something like that. So in those cases also would backtracking help?
Yeah, exactly. It depends on the problem, right? If you are changing, yeah, exactly. In binary tree also, sometimes we need to do backtracking. And I can find some questions for the next session in binary trees that we need backtracking or we don't need backtracking. Okay.
Sure. Thank you.
Yeah. Okay. You're welcome. But it is really if you review the pseudocode solver and this problem, you will see why it will be easier to understand the reason actually I'm not let's say I don't need to raise these guys. Okay, so what is the time complexity of this? I think you guys can calculate that. You can calculate. Actually, we are calculating all possible combinations, right? So it is like solving a probabilistic probability problem. The first one is we have k possible values, and we try all of them in this algorithm. In the second one, we try k minus 1, and the next one we tried k minus 1, right? Do you have any comment?
No, I just.
Yeah, okay. Also, we have k minus 1, k minus 1, k minus 1, k minus 1. We have k options here, and the next one k minus 1 because we cannot use the previous one. So what is the whole numbers? And this is the n houses, right? So it will be k power n will be our time complexity. And that's why I said the brute force usually is exponential, depending on, actually you can also, depending on how many sub-problems we have. Also, you can calculate your time complexity based on your code. As you can see, for every call, we have k sub-problems. So it means that we have for every step, we have k sub-problems. And this is our recursion tree. And again, for each of these guys, we have k. Actually, it is k minus 1, but in terms of big O, I'm talking about the k minus 1. And also, again, we have another one. So this will be k, will be your base of your exponential time complexity. And what will be the power? Will be the depth of your tree. What is the depth of tree? Is 0. This is 0, 1, and it will go over n minus 1. which is the number of houses. So k power n. This is the whole combinations, but I'm missing one important point. Who can, k power n is not accurate. I'm missing one really important point here to calculate the time complexity. K power n is the total combinations, right? But I'm missing some really important part here. Can anyone give any comments? How can I correct it? I have to do something really. Actually, big O is, in terms of big O is k power n is correct. But I wanna, mention another important thing here. For each combination, we do another for loop, right? Actually, if you multiply k times k power n, it will be k power n, right? And I think the k power n is in. I wanted to say we need to multiply k also, but it will be still k power n. Yeah, my bad. It was my. I wanted to talk about another problem because in some cases we have, in recursive calls, I will show you in the next sessions, 2 power n, and we need to multiply by n. But here, I was thinking maybe we have that case here, but we don't have that. So the whole combination, possible combination is, the k power n. Any question, any comments for this part? I want to go and convert this to a memoization.
I have a question. So
Sure.
you calculated the time complexity as k power n, but what my understanding of time complexity is, it's k times k minus 1 times all the way n. So isn't that should be like k minus 1 power n minus 1 times k?
Yeah, actually, this is the exact, this is the, if we wanna, solve, the math problem, we have to say, this is k times k minus power n minus 1, right?
Yeah.
This is the exact, but actually we don't, in a big O, we don't write, the big, but yeah, if you want to do this exactly, this is the exactly time complexity, right? But we write this in terms of big O, k power n, right? This is the upper bound for this guy.
Okay.
But but in most cases, you cannot calculate all of them like this problem. That's why we write, the upper bound. But yeah, definitely, this is, tighter bound, and this is exactly, the exact answer. Any other question? Because I want to go over, convert this to memoization, and then we will want to extend this problem to a little more complicated problem. And you will see, if you know really basic problems, actually this is not basic, this is considered as a hard problem in LeetCode. But for the people who are, really fluent in DP, it is not hard, it is easy. If you solve, the 10, DP problems using top-down approach, you will feel really, really confident in solving DP problems. But if you go bottom up, it will be really crazy, it will get really crazy. And you need lots of, you have to see all the details. But here, you only need to detect what is the sub-problems. In most cases, like binary trees, we have, only 2 sub-problems. It is really easy to handle. In the graphs, grids, or some problems like this, we need some for loops to detect all the neighbors, all the, actually in the grids neighbors we have, in the graph we have also the neighbors. Like in the problems like this, we have all possible colors. In pseudocode, we had all possible numbers for every cell. And in the 8 queens also, we had all possible locations for my current queen. As you can see, we have all possible options for my current situation, which is specified by current index. This is exactly similar to each other. And if you see all of them as a template, as a pattern, it will be easier. But if you solve them as an individual question, it will, even if you solve, 100, 200 problems, you won't have any, enough confidence to solve in every view this kind of problems.
This almost seems, this almost seems like a graph, I mean, I guess you could say it last time. You know what I mean? I mean, you have you
I can't hear you. Can you talk a little louder?
Oh, it almost seems like a graphing problem. I mean, you go for all the nodes in the graph, and then you
exactly.
Yeah.
But here, instead of graph, we have color, right? It is kind of, the simple version of a graph.
Yeah. It's almost like if it's the same color, it's been visited, or you can kind of use that kind of logic on it,
Yes. Actually, sorry. You can see this as a graph, is a chain graph, right? Okay. Even you can see this as a chain graph that, the houses are a row, right? And from 0, 1, 2, 3, 4, and we want to color them, right? And we have a cost. Yeah. We have exactly same, problem in the graph problems, but the graph is not necessarily a row or a chain, right? Okay. And we have all the neighbors. But here, this is really simplified version of the graph problems.
Okay, thank you.
Yeah, exactly. The good, good understanding of, I want to try to map all the problems, all the similar problem. And this is actually the power of the patterns, problem solving patterns. Okay. You don't need to solve as individual problems. They are exactly so similar to each other. So if you don't have any question, I can go and convert to the memoization. You know how easy we can do the memoization. And then, we can do it in only 5 minutes, 3 or 4 minutes right now, because I want to do copying and doing this. But if you code, it will be done in 1 minute, the memoization part. And as you can see, we do k power n combinations. But there are lots of, if you check, this binary tree, I don't want to repeat all the calculations here. For these, sub problems, lots of them are repetitive in terms of our variables. I and previous caller is same for lots of these sub problems. Why? Because let me duplicate this guy. Go here because I want to erase some parts. I did it. Okay, let me do this. So I want to actually erase this guy. Actually, I wanted to use my laptop to increase the speed of the class, to use my IDE to code. But maybe this is like, is better way, because I want to have a feeling of the real classes, to decrease the speed of the class and give enough time to attendees to think about it. I can actually put the code here and talk about it, but I think it is not a really good approach, because if you see the answer, okay, I can explain it. It is like presentation. I don't like that kind of, actually, okay, that kind of teaching. Okay, so we said, we have k power n, for the brute force or recursive, brute force recursive solution. But we know that how many colors we have k, how many houses we have n. And we know that the range of k is 0 to, actually, let's say, this is C. The color range is 0 to k minus 1. And the range of houses, which is I, is 0 to n minus 1. So whole combinations will be n times k, right? If we multiply, how many colors we have, how many, houses. This is the whole values we need to calculate, but we do lots of extra calculations here. That's why we need to save any answer we are calculating inside of the recursive calls. And in the next time, if we call the same subproblem, we just simply return it. So that's why we need to pass a matrix or hash map inside of our recursive call. Right now, I want to go over hash map to see, because I didn't use hash maps in previous sessions, because for memoization part, you can use hash map or a matrix. If you use a hash map, it is simpler because you don't need to worry about the size of your hash map. You simply add append inside of your hash map. But if you want to do the matrix, you have to define it based on the size of row, number of rows, and number of columns. Today, I want to go over, defining a hash map. I want to use hash map for storing the results. So here, the last element is my hash map, which is I'm putting, in Python, if you do the braces, it is a hash map or hash set. Depending on how you are using it, it will be hash map or hash sets. So we are passing this guy here, and let me move this guy a little top. So what will be the first input? Will be a memo. So this is my memo, and I can, all of these calculations here, they don't cost us, right? This is simple, two simple assignments, and this is my base case. So I don't need to put my, checking my hash map value before these guys. So that's why I want to put this here. Before my recursive calls, the body of my recursive call, I need to check if we have the value, the answer of our problem in the memo, we should return it. How we can check that? We can check like this. We will say if in hash map, I want to put tuples of I and previous caller, I and previous caller. I will have a hash map like this. The key will be I and previous caller, and here will be the minimum cost. Okay, so I'm using a hash map instead of matrix. This is my key, this is my value. The reason I'm using tuple, because the tuple is immutable and we don't want to change, the key. So it is better to use tuple. So I will say if memo it is if I and previous caller. We have inside of the memo. If this is in memo, return it. I have the value, because it is not like matrix. We don't have any value. Memo is empty. Our hash map is empty at first, and we are appending in that. So that's why we say if I and previous caller, which is my key, is inside the memo, return the value of memo. Memo at I and previous caller. Simply, we will do that. And at the end, before returning, because we calculated right now here, we are returning the mean cost, right? Oh, I deleted it. Okay. It is bad, in a really bad place. Okay, I will write it. Okay, so here, this is my answer, right? Before returning it, I want to save this inside of the memo. I will write memo at I and previous color is equal to minimum cost. And I will return, let me do this over there, and here we will return. Actually, I can return, either, this or this, doesn't matter. But in order to make it, but actually it is better to return min cost. I don't wanna index. Let me do this with the black color because it is exactly the same as the brute force solution. As you can see, we had only these changes. Also, there is another change. You have to change the signature of your recursive calls. Always, it is really easy to forget this part, especially in doing in the interview. You do all the parts, but you forget updating the signature of your recursive calls. As you can see, it is really easy to convert your brute force to memoization. And if you do these two steps in the interview, definitely you will be accepted for that question. Converting this to a tabulation is also easy, but I prefer to go to the extended version of this problem, which is more exciting. So do you have any question? Actually, we pass a memo, empty memo, which is a hash map. We say if we already calculated this, it means that if we have already answered for I and previous color, why I don't use cost? Because it is constants. The only variables, the values that the input variables that are changing, they are not constant, is I and previous color. Only put them as key for your hash map. I will say if we have already the answer in memo, return it. Pass this here, and before returning, save this in memo, and that's it. And in this way, your time complexity will be, you have a matrix, the memo. Actually, we did a hash map, but actually it is kind of matrix, right? I and C. So we have N here. Let's me write N, and we have K here. So N times K is all of we are calculating all of these values. And for calculating each value, we do a for loop. For calculating all of these guys, we do a for loop, right? And what is the time complexity of this for loop is K. So you have to time K, and this will be time complexity of this problem, which is, you can write, simplify this as order of NK squared. And in the tabulation, we can decrease this to NK, but I don't want to focus on this today. To have extended version, I want to focus on the brute force algorithm approach, and also after that, the memoization. As you can see, we are calculating N times K values, but for every of these values, we do a for loop with the order of K. So don't forget that K. Most people forget that one. And that's it. Any question? And as you can see, the space complexity also, this is the space complexity, this is time. Let me, this is time. And what is the space complexity? Any comments? What is the space complexity?
It's just the memo matrix, correct? And
yes, exactly. And what is that? It is N times K, right?
Yeah.
Yeah, beautiful. And actually we have recursion also, but recursion, the stack space is K, because actually it is N. We go N levels, depth of our, recursion is N, but it is, because it is not our, it is not the worst case. So that's why the memo matrix is our worst case for a space. So the space complexity is order of NK. Any comments? If you have any, actually, as you can see, the memoization part is really straightforward. You don't need to, especially if you want to use the hash map. Because if you want to use a matrix, you have to define a matrix. You have to worry about the number of rows, number of columns. But here, simply define a hash map and put the values inside of that based on index, and that's it. And it is much more easier.
Could you repeat where the extra K comes from in the time complexity?
The time complexity, right? Okay, so we have NK values to calculate, right?
Mm-hmm.
But for each of them, we do a for loop for all colors, right? In this for loop.
Right.
In order to calculate them, we do a for loop here to find the minimum costs. So that's why, for each of those guys, we have a cost of K to finding the minimum costs. Does it make sense?
Yeah.
It's a little, difficult to detect it, but believe me, if you in the interviews, even on site, if you do the recursive, the brute force and talk about the memoization, even talk about it, it is more than enough for interviews. But I doesn't mean don't learn the tabulation. I did, in the previous sessions, how we can convert the memoization to tabulation. But in most cases, if you have a DP problem and start with, the recursive and convert it to memoization, the time is over in the interview. You don't have more than, 20 or 25 minutes. And because you did really very well in those parts, and you will have, the maximum score for that interview. Okay, that's why I strongly recommend do the top down. Unless the interviewer asks you, you have to do the iterative solution and you do the bottom up. And if that's the case, I again recommend do the step one, brute force, and the memoization, then convert the memoization to tabulation, which is a little harder than the converting the brute force to memoization. And in the way I'm teaching, actually, in the textbooks, they rephrase the problem, they do all of the calculations from the beginning. But I just convert this code you see here directly to the tabulation. But this session, I think it is better to go to the next problem, which is extension of this, and it is second to the last problem of the LeetCode, because it was the hardest problem of the last contest. Every week I check the contest problems. I try to teach the most hard problem of the contest, not only the hard problems, the problems that have really good lessons for my students, for my the even meetup attendees. Any question? Let me check my Zoom and the chat part. Maybe we have some. Okay. Oh, raise hand. I think someone. Did you ask your questions?
Oh, I did have before.
Sorry, I sorry, I don't know. I'm so sorry, and I didn't see that, because I'm switching between the windows. This is I think the bug of the Zoom. It should show me, even if I'm in the other others. Okay, if you have any question, please ask right now.
I do not have a question, but could you take a sample input, and is it possible that could you explain the memoization with that sample input instead of n in case?
Sorry, so can you? I didn't get your question. Can you say again?
Is it possible that Can you explain the memoization using a sample input instead of using n and case?
You mean, you know, you need to go by example, right? You know, to see what's happening.
Yes.
But, you know, actually, for the recursive calls, if you want to go one by one to see what's happening, and you have to go inside of all of the recursions, right? It takes a lot of time, you know. Actually, yeah. I was trying to recommend you to do this for once, but this is the magic of the recursive calls. You don't need to worry about what's happening. If you formulate your, you know, recursive, you know, formulas in the correct way and the base cases, it will give you, you know, the correct answer. But when we convert this to the memoiz, you know, the tabulation, you see what's happening. You know, I will do the next session, but if we go one by one, all of them, it takes a lot of time. But I was trying to recommend you to do this, you know, for, you know, one time, but with really small example. Don't go over, you know, the, let's say n should be only 2 or 3, and k should be 1 or 2. Go ahead and do that, and you will see what's happening. But here, I think I prefer to go to the next problem, because you know, for the first, for a couple of problems, you need to do that to understand what's going on. But after that, you don't need to do that. You need to see the helper or recursive function as a black box that returns you your objective, and see that as a function, not as a recursive function. You can see this as a function that gives you the cost of that sub problem, and then based on that, how you can calculate the objective of your current problem, like we do here, right? We say, I have the minimum cost of, you know, my house is starting with I+1, and I have the cost of my current, you know, the coloring of my current house with the color C. How can I update my minimum cost? Like this. I have to add this and then update my minimum cost. Okay. Sometimes we need to make or sometimes we need to minus, or, you know, we do different, you know, operations depending on the definition of the problem. Okay. Okay, let's go and define the next problem. If you don't have any question, maybe in the next sessions, I will go over, you know, one by example to show you what's going on with a little smaller problem. Okay. Okay, so in the problem paint house number 3, it is so similar to the previous problem, but with some, you know, more conditions, more constraints. We have, let's say, given is n houses, like, you know, we did, you know, exactly in the previous one. Also, we have k colors, but the colors are starting from 1 to k. In the interviews, they change the starting value from 0 to 1 to show you how you can handle that. It is really common in the interviews. Maybe you solve some problem, you know, the colors are, you know, like the previous problem is starting from 0 to k minus 1, but they say the colors are 1, 2, 3, 4. And we don't have color 0 in this problem. They change the definitions in terms of, you know, the numbers like that. And so we have n houses, and also we have a houses array. We have an array of houses with the length of n, but the initial value, if it is 0, it means that houses are not painted yet, but some of the houses can be already painted. For example, let's say, you know, we have let's say the K is equal to 3, it means that we have colors 1, 2, and 3. Let's say some of them are already colors. And let's say this, I'm going by example because you know that, oh, that we don't have 4. And let's say this is 2. We have colored all of these guys. But 0 means house needs painting. Okay, so one more assumption, so far, that some of houses are already painted. So we need an array showing which houses are painted. But in the previous problem, we didn't have any array. We had only a number that we have in houses. Okay, so we have this. And also exactly same as the previous problem, we have a cost matrix, which is n. The dimensions are n times k, which is the cost of coloring. This is exactly the same as the previous problem, but you should be aware of the indices for colors. Index 0 means color 1. Index 1 means color 2. Index 2 means color 3, because of the definition we have here. The colors are labeled from 1 to k, not 0 to k minus 1. So we have also the cost matrix. And what is the object? And we have another definition, which is neighborhoods. Neighborhood. What does the neighborhood mean? Let's say I have, the painted, in this example, I have painted all of them. Let's say we have 1, 1, 2, 3, 2, 2, 1, 3. How many neighborhoods we have here? All the same colors, near, back to back are a neighborhood. So for this guy, we have a neighborhood here. We have a neighborhood here because we don't have it. Also, we have a neighborhood here. This is another neighborhood. This is another neighborhood, and this. How many neighborhoods we have? 1, 2, 3, 4, 5, 6. So the number of neighborhoods here is equal to 6. Okay. So these are assumptions. So we have 2 more assumptions here. We can have already painted house. We can have also, we have another definition, which is neighborhood. The previous one we said neighbor houses cannot be cannot have same color. So what is the objective here? Sorry, we have another assumption, which is targets. Target is the number of neighborhoods we want to have. This is another input. So we want to have, for example, 10 neighborhoods. We want to color, and the result of the painting should give us the, let's say, T neighborhoods. And what is the objective? Find minimum cost of painting all houses so that number of neighborhoods is equal to targets. So as you can see, right now our conditional is a little complicated, a little more complicated. And we have our input is also a little more complicated, but it is so similar to the previous one in terms of approach. We need a little more variables, but we can handle that if you learn if you have learned the previous one. Let me check all device here. Okay. So any question so far about the problem? Because if you don't understand, if you don't understand the problem definition, it will be much more difficult to understand the solution, right? If you have any question about the assumptions, please ask. No question? Okay, good. I think because we solved the previous problem, now it is much more clear for you guys. So let's go and do the figure out what is our sub problems, how we can handle the sub problems. If you remember the last problem, we said we need an index I. Let's say I have this is my houses. Now we have a houses array as input 0, 1, 2, 3, 4, 5, 6, 7, 8. And some of them are 0 and some of them are already colored. And if it is already colored, we don't need to color it, right? We need only escape it. So let's say we have 0, 0, 1, 0, 0, 0, 2, 0, 3. Okay. Exactly same as previous one. I'm going I'm in index I. How many options I have? The previous one we said, I want to color this with K colors, right? But right now, exactly we have this if it is 0. But if it is not 0, I don't need to color that one, right? I just simply go to the next neighbor, next house, right? So it means that in the highest level, I have to check houses I. I have two cases, if it is 0 or if it is not 0. If it is not 0, simply I will go increase I 1 unit, right? Because I don't need to color it. If it is 0, I have to try all possible colors. So similar to previous problem. But what I'm missing here, the number of neighborhoods, right? So let's say we have a target as the input. This is the number of neighborhoods I have to reach to this guy. And let's say this is my, I want to reach to this guy. I want to go in, I want to have this as an input. And every time I detect I have a new neighborhood, I want to decrease it. At the end, I will check if the target is 0, it means that the combination satisfies the target constraints, right? So it means that if I want to go 1 unit, let's say here, say I'm saying house I is already painted. Let's say we are here, I is here. It is already painted. How can I detect how to update the targets? I have to detect if we create using this one a new neighborhood or not. How can I detect that? Any comments? I don't want to go really without your comments. Let's say I colored these guys before. I have some values here. Let's say this is 2 and this is 1. I want to know, let me make it a little better, 2. My index is pointing 2 houses 2, and it is already painted. I want to know if it creates a new neighborhood or not. If I check this value with the previous one, if it is different than the previous color, it means that we create a new neighborhood, which is 2 and 2. it means that I need previous one, I need a previous caller to detect if the current caller is different than the previous caller. It means that I have to decrease the target by 1. So whenever we want to call our recursive calls, we have 3 variables, 3 parameters. We want to increase I. We need to know that the previous caller to update the target. Also, we need target to pass in all of recursive calls. And here also, when we try all possible callers, for each caller we put, we have to update targets. If we are creating a new neighborhood, we have to decrease targets by 1. Okay, so this part, the sub-problems is exactly equal to the previous problem, but we need to update one more variable, which is targets. And this part, which is already painted, we go to the next one, but we have to update the previous caller, also the target if we create a new neighborhood. Any comments for this part, any question? If you see the code, it will make more sense for you guys, I think. But you know, because we started with the previous problem, I hope this will make more sense for you guys. Any feedback, any question? Okay. I don't see you guys. I don't know how you are feeling right now for this problem. Okay. So as you see, you know, we have 2 high levels. Let's go and write the code and you will see how we are handling these parts. So same as the previous problem, I will have a top level, which is define minimum cost. We have houses. Right now we have also another input, which is because we can have already painted. We have a cost matrix. We have a target. Okay, these are our inputs. And we will return helper, which is our recursive function, which is we need houses, cost, and targets as original initial inputs. But we need 2 more inputs, right? Index, which is 0 initial index, and the previous caller. Right now, because 0 means it is not painted, we can use 0 as previous caller. The previous example problem, 0 was a caller, but right now 0 is not a caller. Caller is 1, 2, 3, 2, K. Okay, so the initial value will be this. So this is index. This is previous caller. So let's go ahead and write the helper. Houses, cost matrix, target, I, and previous caller. So first of all, I went ahead and check the len of houses will be the number of houses. K will be len of cost 0. Number of columns of cost is number of colors. And I want to put the base case after I'm writing my recursive parts. If you remember, we said we have two high-level conditions, right? It was if houses I is not equal to 0, it means if it is already painted. Okay, it is already painted. What should I do? I should call the recursive call with updated, I have to increase I, and I have to update previous color and on the targets, right? So let's go in, I will write here, return helper houses costs, and the targets will be, we have to check if the targets, if the current color is equal to, well, let me do this before this guy, and then because we need, you know, the update color, the targets, right? I would say if houses I, which is the color of, you know, the current house, is not equal to the previous color, it means that we have a new neighborhood, right? We see a new neighborhood. If we have this, we have to decrease target by 1 because we created a, you know, we have a new neighborhood, and then we have to return helper. I could write this in 1 line, but I want to make the code more readable actually than, you know, really fancy. So I will call helper houses costs updated targets. I will go 1 forward, and the previous color will be the current color, right? The current color is houses I. So we did this for helper. I'm just, you know, we are, I hope we are in recording. Let me check this. Yes, it was really, okay. So this is the first case, right? We did this. If it is not, we don't need to write else because we have return here. If we are, you know, here, it means the houses is 0. Okay. If it is 0, we need to do exactly the previous operations we did. Do you remember we said, you know, we need to define a minimum cost as the initial value as a float of infinity. So this is my initial minimum cost. Actually, I'm trying all possible colors for this, for the current house. And I will go for C, which is my color in range. You have to be careful here. Colors are labeled from 1 to K, right? So that's why I'm writing here 1 and K plus 1. You can do 0 to, because the reason I'm doing this, because the cost matrix, you will see right now, you know, because the labels are from 1 to K. That's why I'm doing the exactly based on the definition of the problem. So we have this here, and we want to go over our recursive call, right? But before that, we have to update the targets. I want to update the targets, and I can write here, if I want to define a new target, I will explain why I'm doing this here. new target. The initial value is the current target, right? But I want to check if I have to update it with target -1 or not. I'm checking if the current color, which is C, we did exactly like this, you know, the previous problem, is not equal to previous color. If it is not equal to previous color, I have to update my new target equal to target -1. And I will explain why I'm doing this, why I didn't do like this. And there is a really good lesson for that part, why I'm using this kind of, I'm defining a new variable instead of using that target. So I'm trying here, let's write here, you know, the comments, it is really helpful. Try all possible colors. We are trying all of them. So we updated target, and now it's time to call all over, you know, the recursive calls. Do you remember, you know, the previous problem we said current cost will be equal to the cost of current color will be cost of I, which is my house, right? And the current color. The color is C, but C, because C is starting from 1 to k+1, and the indices are starting from 0 to k-1, I have to write C-1. The current cost will be the cost of my current, you know, the painting of my house with this color, plus this is exactly the same as previous problem. That's why I don't want to explain more. Helper will be houses cost. New targets, we updated our target. Maybe it is decreased by 1. I+1. And what is the previous color? The current color we are you know, selecting, right? Which is C. We are calling this helper, and at each round, also we have to update our minimum cost, which is minimum cost and current cost. And that's it, right? And then at the end, I will return minimum cost. And same as previous problem, we need to go and write the base case. Targets is changing. I also is changing. They are important because I shouldn't go, you know, out of range, and target should be 0 at the end, right? That's why I can add the base case here. If I is equal to n, what should I do? I will say if the target is 0, I have to return 0, right? Because if I is n and target is 0, it means the cost is 0, and I don't need to color anything, right? Well, let's say that target is not 0, and we didn't meet, we didn't, you know, satisfy the targets. In the question that said if we don't have the answer, we have to return infinity, right? So I will talk about this, you know, a little more. If I is n, and if target is equal to 0, it means that we can return 0 because we are accumulating in the recursive calls, all of them, right? This part is exactly what similar to the previous problem. Well, let's say it is not 0. It means that this combination, this recursions, this chain of recursions, we finished it, but target is not 0. What should I return? I want to return something that won't have any impact in my operation of the minimum. That's why I want to return infinity, so that answer will be deleted. It won't have any impact in my final answer. So that's why if it is target is 0, I will return 0. Else I will return float infinity, because it is a failure, right? The cost is, for the failure, we put cost of infinity, and in the minimum operation, it will be omitted. It will be deleted. Any other combination will be winner in this minimum operation. So, and this is our base case. Okay. So, as you can see, we handled more variables, more constraints. We had 2 more constraints. That's why we have houses here. And for the neighborhoods, we have more checking here and here to update our targets. And that's it. We need only one. This is the only extra thing we did here because of the neighborhood definition. And the reason I did here like this, I didn't want to change targets because I want to have targets, which is my input for all of these recursive calls. This is exactly, I did this to avoid any backtracking. Let's say I didn't do this, if I update the target here, the next round, I want to go to the next call, I need the original target. I have to revert the targets. I needed to put another if statement after this recursive call to check if I decrease this, before this recursive call, I need to increase it, revert it. But if I didn't decrease it, I have to, I didn't increase it, I can pass this, with the same value. This is another example of, how we can bypass backtracking, especially if we have scalar values. Because using a new target as an integer doesn't cost us space complexity. It doesn't cost us any space, so we can simply do that. Because for any recursive call, we need the original target. We don't need to update the target value. So that's why I keep the target. It just calculate a new target and put it here. In the next round, I'm going in this way. And
didn't you have new target in the previous
sorry
call? Shouldn't define a new target in the previous recursive.
The reason I'm not using here, because we are returning here, right? We don't come here. If we are inside of this if statement, right? We have only one recursive call, and we shouldn't worry about the new target here. We call only once, right? But here, let's say I wanna.
Yeah, but that recursive call will be called many times, right? So,
but yeah, but you have to check if you have several calls inside of the function, right? You are calling this and you need to update the targets, right? We don't, in this part, in this if statement, only we call once the helper, right? But this part, we call the helper for k times.
Okay, I see.
Yeah, this is the, exactly the, the really important lesson of, the backtracking. If you call once and return, okay, you don't worry about anything, right? But if you are calling, different calls, and the most difficult is when we do the for loop. If you do, like binary trees, you do the left call and the right, you see you have sequential calling. But here, because we do for loop, maybe you people you don't see that. We do lots of recursive calls. If we change some really important parameters, we don't need to see the impact in the next calls. Okay. And actually in the LeetCode, they said if we don't have any answer, because we can have a target that we cannot color the houses to meet this target, return -1. But right now we are returning infinity if we don't have any answer. I need to put infinity here to handle my the problem in a successfully in this mean operation. But for final answer I want to return, I have to check here if it is infinity, I will return -1. But if it is not, I will return the answer. Only in order to pass all test cases of your actually if you want to code this in the LeetCode. But actually this solution will not pass the LeetCode test cases. It will be time exceeded. You will have time exceeded message, because this is exponential and you have to update this with memoization. But because we don't have time today, I think it is a really good practice for you guys to do this as a homework, to how you can convert this to the memoization. And that how to do that. It is a little, there is a delicate point in converting this to the memoization, but I prefer don't talk about that delicate point. Please go and try to convert this code to the memoization. And if you have any question, please ask me and I will help you. You need to do one more thing that we did in the previous question. And I think you will detect that. So that's why here, because we can have infinity, I put this in answer, and then I will return. I will say if answer is equal to float of infinity. It is really return -1. This is only because of the the constraint of the LeetCodes. In the real interviews, you don't need to. You only need to talk about how can I return this one. You can return infinity. Infinity is also true. So, but if it is not infinity, we will return the answer, which is the value as integer, a limited integer value. Okay. This is exactly the time complexity is a little different here because we have 3 variables: targets, I, and previous caller. And what is the range of targets? The target is going from 0 to, let's say, t -1. Sorry, to t. Let's say I've solved the memoization solution. The target is going to 0 to t, I is going 0 to n -1, and pre-color, or let's say color, is from 0 to k -1. So we will have 3-dimension matrix if we do the memoization. It is really good practice, but nothing is new here, right? You can use the hash map, and the tuple will be, let's say, target, I, and color. Your tuple will be these guys. You shouldn't worry about the dimension of your matrix. You will do exactly equal to the previous one, and whole combinations will be T times N times K. But as I said, for each combination, similar to the previous one, we have K for calculating all the possible combinations. So we will have times K. So order will be T N K squared for memoization parts. Actually, we can decrease this for T and K if we use tabulation. And you can think about it, but the next session I will go over converting these guys to the memoization, the tabulation, or I will go to the new problems, but I will focus only the tabulation parts. But as I said before, it is more than enough to write, the brute force and convert to the memoization. All, top tier companies will accept you in the interview if you do in these 2 steps correctly. And don't worry about the tabulation. I will teach that as I teach this, before. I taught this before, but I think this is enough for today. And but actually, this time complexity is not time complexity of the brute force. It is for memoization. This is memoization in time complexity. Please do that. If you have any question, please ask me in the meetups, in the comments. Also, the last session I gave, my emails to you guys, and if you have any question, you can ask through email, or you can go on the Facebook of my Facebook page.